Welcome to my channel. In this video, we shall be looking at gravitation. Let's look at the learning outcome. In this video, you will understand acceleration due to gravity. You will know what gravitational field is all about. You will state Newton's law of universal gravitation. And you will understand gravitational field strength or intensity. Okay, let's start. Every object falls to the earth when being thrown up. For instance, if I throw this up, you discover it will fall back. And this is as a result of gravity. It's as a result of what? Gravity. And the falling of an object under the influence of gravity is called free fall. That I throw this up, it fall down as a result of gravity. So the influence of the gravity on every object being thrown, we call it free fall. And the rate at which the object that is falling experiences this gravity is called acceleration. Acceleration due to gravity. Acceleration due to gravity. We normally represent it with small letter g. So the SI unit of acceleration due to gravity, the SI unit of g is meter per second square. And it varies from one point to another. We shall be looking at it in the course of this class. So we can say that gravity is a force that pulls an object. That force that pulls an object is called gravity. While gravitational acceleration is the rate at which the object comes towards the object pulling it. So we can say that acceleration due to gravity is caused by gravity. Let's look at gravitational field. Gravitational field. Gravitational field is a region in space where a body experiences a force field. And the force field we are talking about is gravitational attraction. So a region in space, a region where gravitational force is experienced, we call it gravitational field. And I want to remind us that gravitational field is among the field in nature. We have electric field, we have magnetic field. So an object in electric field, we experience electric force. Object in magnetic field, we experience magnetic force. So we are talking of gravitational field. It's a region where a body experiences a gravitational force or gravitational attraction. So it's a vector quantity. Gravitational field is a vector quantity. And we can say that Earth gravitational field is directed towards the center of the Earth and possesses gravitational field strength. Gravitational field strength called acceleration due to gravity. So any object in the Earth gravitational field, we experience gravitational attraction. We experience gravitational field strength, what we call acceleration due to gravity. Okay, let's make progress. So let's look at Newton's law. Newton's law of universal Newton's law of universal gravitation. If you have two objects of mass m1, another object of mass m2, separated by a distance r, the force of attraction between them, F, is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. So if we remove the constant of proportionality, introduce a constant G, which we call universal gravitational constant, we will have G m1 m2 over r squared. So G is called universal gravitational constant, and its value is 6.67 times 10 raised to power minus 11 newtons per kilogram square. So according to Newton's law of universal gravitation, it states that the force of attraction between two masses, m1, m2, separated by a distance r, is directly proportional to the product of the masses and inversely proportional to the square of the distance between them. So mathematically, we can state that Newton's law of universal gravitation can be written mathematically as this. So we remove the constant of proportionality, introduce equality sign, we have this expression, where G is a universal gravitational constant. So this is the mathematical statement of Newton's law of universal gravitation. Let's use this expression to solve some example so that we can better understand what we are saying. Example, let me read out the question. A man of mass 95 kilograms is dancing with his wife of mass 52 kilograms. Assuming that each person's mass is concentrated at their respective center of mass, which is separated by 28 centimeters, what is the gravitational attraction between them? Which person has the greatest gravitational attraction towards the other? Solution. Say a man and his wife, the mass of the man 95 kilograms, mass of the wife 52 kilograms, the distance of separation 28 centimeters, which is 0.28 meter. So we have to find the gravitational attraction between them. So using this expression, F, gravitational attraction between two objects, like we said, is equal to G, mass of the man, mass of his wife, over the distance of separation squared. So this G, see this, the value, let's substitute 6.67 times 10 to power minus 11 So if we simplify, we will have 4.167 times 10 raised to power 6 Newton. So this is the gravitational attraction between the man and his wife. So this is the first part of the equation. The second part says, which person has the greatest gravitational attraction? So to answer this, by Newton's third law, from Newton's third law, we say action and reaction is what? Equal and opposite. So both of them have the same gravitational attraction towards each other. So the gravitational attraction, we are using Newton's third law to answer that. The force with which the man attracts the woman, that action, is the same. the reaction from the woman. So by Newton's third law of motion, it says action and reaction, they are always equal and opposite. So which person has the greatest gravitational attraction towards the other? The answer to it is that both have the same gravitational attraction towards each other. Are we together? So this is simple. This is how we calculate the force of attraction using Newton's law of universal gravitation. I hope no challenge. Okay, let's make progress. Let's look at another example. Okay, let me read out the question. What is the gravitational force between two objects of mass 8 kg and 70 kg at a distance of 1 meter apart? Take universal gravitational constant to be 6.67 times 10 raised to power minus 11. So we have another question. Solution. Using this expression, if we substitute, so if we simplify this, we will have, so for the two masses, we have two masses. One is 80 kilogram, another one is 70 kilogram, separated by a distance 1.0 meter. So we are to calculate the force of attraction. So we have simplified. This is the force of attraction between them. So I hope with this, you can solve any other problems using Newton's law of universal gravitation. Okay, let's make progress. Let's look at gravitational field strength. The gravitational field strength at a point in a gravitational field is defined as the force exerted on a unit mass placed at that point. Mathematically, gravitational field strength G, we say it is the force, gravitational force of attraction per unit mass. Let's call this equation 1. Gravitational field strength, based on this, the unit will be what? Unit of force is Newton, unit of mass is kilogram. So the unit of gravitational field strength is Newton per kilogram. And gravitational field strength varies from one point to another, but it's approximately 9.8 Newton per kilogram or meter per second square. So we have two units for gravitational field strength, either Newton per kilogram or meter per second square. and it is called acceleration due to gravity. So gravitational field strength is also called acceleration due to gravity, G, and it has approximate value of 9.8 Newton per kilogram or meter per seconds. Okay, if we consider two masses, let's say M2, another mass, M1, the force with which M2 is being attracted by M1, separated by distance R, we can write that from Newton's law of universal gravitation, that F equal to G M2 M1 over R squared. Then, from our definition of gravitational field strength, we can say that the force per unit mass, is given by F over M2. And this is equal to G M2 M1 over R squared. So from here, we can have G M1 over R squared. So another relationship for G is G M1 over R squared. So this is another expression for G. So we are saying that if you have two masses, M2, M1, and M2 is being attracted by mass M1, and both masses are separated by the distance R. From Newton's law of universal gravitation, we have this expression. I believe we are familiar with this expression. Yes. So from here, we can say that the gravitational field strength, which is the force per unit area, the gravitational field strength that mass A, mass M1 attract mass M2 with. See here, force, the force of 2 by 1, the force with which M2 is being attracted to M1 is given by this expression. So in place of this F, we substitute this equation, we have this. So from here, we move this way. And M2 will cancel. So we are left with this. So we are saying that beside this expression for gravitational field strength, we can also use this expression to calculate the gravitational field strength. Are we together? Okay, we shall be using this as we make progress. And this expression gives us the relationship between gravitational field strength and universal gravitational constant. So this expression gives us the relationship between gravitational field strength and universal gravitational constant. Okay, we have seen that the approximate value of gravitational field strength is 9.8 meter per second or Newton per kilogram. And this value varies from one point to another. So let's look at factors that influence variation of acceleration due to gravity, or what we call gravitational field strength or intensity. Let's look at factors that affect it. So We are looking at factors influencing variation of G. Several factors influence the variation of gravitational field strength or acceleration due to gravity. One of it is altitude. Altitude. When a person moves higher from the surface of the earth, the distance between the person and the surface of the earth varies. And this distance affects gravitational due to gravity. For instance, we say from the force of attraction G, M1, M2 over R, based on this, the gravitational force of attraction is inversely related to the distance. So for somebody that moves away from the surface of the earth, or even below, this affects the gravitational field strength or the force of attraction. So altitude is one of the factors that influence variation of acceleration due to gravity. So for somebody who is above sea level, and even below sea level, above sea level, below sea level, there is slight variation of about 0.01 meter per second square. So the variation is not all that significant, but all we are saying is that some factors like altitude influence variation of acceleration due to gravity. The second factor is latitude, the location, latitude, and the rotation of the earth also influence latitude and earth rotation. So the earth is spherical in shape, flattened at both ends. So this has significant influence also on the acceleration due to gravity. So these are the two main factors that influence acceleration due to gravity. And the acceleration due to gravity varies from one astronomical object to another. Let's look at astronomical object or celestial body. Celestial body and acceleration due to gravity. For the case of Earth, we have seen that the acceleration due to gravity is 9.8 meter approximately. Let's look at the case of Moon. The case of Moon is 1.62 meter per second. For other planets like Mars, the acceleration due to gravity is 3.17. Then for other planets, Jupiter has acceleration due to gravity of this. Venus, so these are acceleration due to gravity for celestial body. So it is not only Earth that has, planet Earth that has acceleration due to gravity. We have seen other planets and their various value for acceleration due to gravity. The next thing we want to look at is gravitational potential. gravitational potential represented with symbol psi. So gravitational potential at a point in gravitational field is defined as the work done in bringing a unit mass from infinity to that point. So mathematically, gravitational potential is the work done in bringing a unit mass from infinity to that point. So mathematically, gravitational potential is given by equation 1. And the SI unit is in joule per kilogram. So that is the unit of gravitational potential. And if we see equation 1, the negative sign indicates that work has been done against the potential. Or in other words, we can say the potential at infinity is greater than the potential at a point near the source mass. Okay, let's look at an example where we can calculate gravitational potential. Example, let me read out the question. Determine the gravitational potential of a point at a height of 40 kilometers above the Earth's surface. Take mass of the Earth, radius of the Earth, and gravitational constant. The values are given. So solution, mass of the Earth is given as 6.0 times 10 radius of the Earth These are the given parameter. From the question, we have that the distance will be the height of the Earth plus the radius, the height of the object plus the radius of the Earth. So we have 4,000 plus 6.4 times 10 to the power 6. So using the expression, say gravitational potential is given by this expression minus G m over R. So if you substitute, so if we simplify, this, this is the gravitational potential. So in the equation, we were asked to determine the gravitational potential of a point at a height of 40 kilometers. We convert to meter. above the Earth's surface. So we substitute using this expression for gravitational potential, and we simplify this distance. We got it, the height above the surface of the Earth plus the radius of the Earth. And when we simplify, we get this expression. It's in megajoule per kilogram. I hope there is no challenge with that. So this distance r is the distance from the center of mass of the Earth to the point 40 kilometers above the Earth's surface. So this is how we go about problems or calculation of this nature. I believe it's not difficult. Okay, we have looked at gravitational potential. Let's look at gravitational potential energy. Gravitational potential energy, so that we'll see whether they are the same or they are different. Okay, the gravitational potential energy of mass m at a point in a gravitational field is defined as the work done in bringing the mass from infinity to that point. So we are saying that gravitational potential energy of a body of mass m at a point in a gravitational field is defined as the work done in bringing the mass from infinity to that point. So gravitational potential energy is equal to the mass times the gravitational potential. And we have seen that gravitational potential is given by minus g m over r times this m. So we have gravitational potential energy to be given by this expression. Let's call this equation 2. So the unit of gravitational potential energy, like every other energy, the unit is joule. The SI unit is what? Joule. So based on this, is there any similarity or difference between gravitational potential energy? Let's look at it. Gravitational potential energy, you say, is the work done to bring a unit mass from infinity to a point. Work done bringing a unit mass from infinity to a point. Why gravitational potential energy is the work done to bring a mass from infinity to a point. I hope we have seen the difference between the gravitational potential and gravitational potential energy. So thank you very much. So far, we try to look at acceleration due to gravity, free fall, gravity, and try to differentiate gravitational potential, Newton's law of universal gravitation, and to look at the difference between gravitational potential and gravitational potential energy. In our next class, we shall be looking at escape velocity and the Kepler's law of planetary motion. We shall also consider period and speed of satellites using Kepler's law. Thank you very much for watching. Please like, share, and subscribe to my channel for more interesting videos.